So the sun is 99.8% of the mass of the solar system. Jupiter is about 0.1%, and everything else is miscellaneous. Now, even if you were to burn Jupiter in a thermonuclear reactor, the amount of energy produced by the sun would still round up to 100%, because Jupiter is only 0.1%. Actually, solar is the biggest thing in China. So I believe China's production capacity on solar is 1,500 gigawatts a year, and they're deploying over 1,000 gigawatts a year of solar. Now, for continuous solar load, you divide that by roughly, I don't know, 4 or 5. Call it that's around 250 gigawatts of steady state power paired with batteries. And that's a very big number. That's half of the average power usage in the US.
Right.
So US power usage on average is 500 gigawatts. Right. China, just in solar, just in solar that can provide steady state power, and batteries can do half of the US electricity output per year just with solar. Solar is by far the biggest source of energy. And actually, when you look beyond, or even on Earth, but certainly beyond Earth, the sun rounds up to 100% of all energy. This is an important thing to consider. So the sun is 99.8% of the mass of the solar system. Jupiter is about 0.1%, and everything else is miscellaneous. Now, even if you were to burn Jupiter in a thermonuclear reactor, the amount of energy produced by the sun would still round up to 100%, because Jupiter is only 0.1%. If you teleported 3 more Jupiters into our solar system, and burnt 3 more Jupiters and everything else in the solar system, the sun's energy would still round up to 100%. Mm-hmm. So it's really all about the sun. And that's why one of the things we'll be doing with SpaceX within a few years is launching solar-powered AI satellites.
Right.
Because the space is really the source of immense power, and then you don't need to take up any room on Earth. There's so much room in space, and you can scale to enormous. I mean, you can scale to, I think, ultimately hundreds of terawatts a year.
You and I have had these conversations before, but why don't you tell the audience, what would it take for the United States, and what type of geography would it take to have that solar field to electrify the United States? And then let me ask a question, why aren't we doing it?
Yeah, so, I mean, I guess a rough way to think about it is 100 miles by 100 miles, or call it, I don't know, 160 kilometers by 160 kilometers of solar is enough to power the entire United States. So, 100 mile by 100 mile area is, I mean, you could take basically a small corner of Utah, Nevada, New Mexico. Obviously, you wouldn't want it all in one place, but it is a very small percentage of the area of the U.S. to generate all of the electricity that the U.S. uses. And the same is true, actually, I mean, for Europe. You could take a small part, you could take relatively unpopulated areas of, say, Spain and Sicily, and generate all of the electricity power that Europe needs.
So why don't you think that there's a movement towards that here and in the United States?
Well, there is.
As it is in China.
Well, unfortunately, in the U.S., the tariff barriers for solar are extremely high, and that makes the economics of deploying solar so artificially high, because China makes almost all the solar,
What would it take for Europe or the U.S. to build it commercially, if it's that scale?
Yeah, I think. Well, I can tell you what we're going to do. At SpaceX and Tesla is we're building up large-scale solar
Right.
So the SpaceX and Tesla teams both separately are working to build to 100 gigawatts a year of solar power in the U.S., of manufactured solar power. That'll probably take us, I don't know, about 3 years or something. But these are pretty big numbers.